number of people were struggling with the adiabatic lapse rate activities, and so I thought I'd make this video. First, I'll talk about this part. The parts before this, where it talks about lifting mechanisms, in my opinion, is pretty self-explanatory. You just read and label stuff, but I wanted to go over this part. In order to complete this part, you're going to need this chart from the previous week. The humidity activity. If you haven't created one, you'll need to create one. So this is in the atmospheric humidity one. So you're supposed to make this little chart. And we need that so we can figure out what the water vapor capacity is. So we can figure out what the lifting condensation level is, at what elevation clouds will form or the air is saturated. Okay, so it says calculate, assume that the unsaturated air parcel located at sea level has an initial temperature of 17 degrees and a specific humidity of 4 kilograms of water. So the prevailing westerlies are forcing the air parcel eastward toward the western slope of the Sierras. Calculate the relative humidity and the dew point temperature of the air parcel at 0 meters. Show your work. Okay, so first thing, relative humidity, if you recall, is content divided by capacity times 100. So we're going to look at our little chart here, and we're going to go to 17 degrees, which for our intents and purposes, we'll say is between 15 and 20. And so we'll just call it 12. So its capacity is 12. The content is 4. So 4 divided by 12 times 100 equals 33%. So that's the relative humidity. So the dew point temperature is at what temperature will the air reach 4 kilograms of water vapor. So at what temperature, we're just going to kind of do this thing. Water vapor capacity of 4. It's above 1. So we'll just call it about 1 degree. So I use the opposite side. So I go to here and I say this is 4, and then I go across, and here's 0. So it's just past that spot where it intersects. So we'll just call that about 1. So approximately 1. Okay. As the air rises and cools, the humidity gets greater and greater, and the air eventually reaches 100% humidity. This is called the lifting condensation level. At this altitude, this is where clouds start to form, and it's the bottom of the cloud. So at what elevation will the clouds start to form? Calculate the lifting condensation level for this air parcel using the preceding formula and show your work. Okay, so this says air temperature minus dew point air temperature divided by the dry adiabatic rate in hundreds of meters. Sorry, thousands of meters. Sorry. Okay, so the air temperature is 17. Get that from the question. 17. The dew point temperature, we figured looking at the chart that it was 1. Okay. Divided by 10 degrees per 1,000 meters. So that would be 16 divided by 10 is equal to 1.6 times 1,000. And so we end up with 1,600 meters. So this is just max in this particular case. All right, so then the next thing it asks us to do is calculate the expected temperature of the air parcel at the ridge, which is 4,000 meters. Don't forget to calculate the dry adiabatic rate of the air before it reaches the lifting condensation level and the saturated adiabatic rate as it continues to rise to the peak. If you don't understand what these words are, look at the other video that I already made where I talk about lifting condensation level, saturated adiabatic rates, and things like that. or you can watch this guided practice video by scanning this QR code. All right, so assuming that we're on the same page with that, the first question asks us what temperature at the lifting condensation level. What is the temperature in degrees? Well, we're still talking about the same place, so it's still going to be that 1 degree Celsius. So now we just need to figure out what the temperature is at 4,000 meters. All right, so we already said here that the change in elevation, so 1,600 meters minus the 0 meters is 1,600 meters. So the change in elevation is 10 degrees per Celsius divided by 1,600 divided by 1,000. So, all right, so we determined that we need to go up 1,600 feet in order to go from the current temperature of 17 to the temperature now. So we go with 1,600 meters. And we were at 0 meters. So minus 0 meters is equal to 1,600 meters. That's how much we've gone up. The change in temperature is 10 degrees per 1,000 meters. So it's 10 degrees per 1,000 meters times 1,600 divided by 1,000, because that's how much it goes up. It goes up 10 degrees. So per 1,000, I could put it here too, but I'm just going to put it over here. So it's going to go down 16 degrees, obviously. So 16 minus 17, we already determined is 1 degree Celsius, which we already figured out. We did it up there. All right, so now we need to figure out how much we're changing. So we're going to go from 4,000 meters minus, because we're at the lifting condensation level, okay? So we're at 1,600. So the difference in that elevation is 2,400 meters. So 4,000, that's where we want to be. And the lifting condensation level is 1,600 meters in this particular example. So we've changed 2,400 meters. And the wet or saturated adiabatic rate is 6 degrees. So dry adiabatic is 10 degrees, saturated is 6 degrees. So this time we're going to take our number. So we're going to say 6 degrees, right, times the difference in elevation, 2,400 meters, divided by 1,000. 14.4 degrees Celsius. So that's how much we're going to take off. The temperature used to be 1, so we say 1 minus 14.4 equals negative 13.4 degrees Celsius. So this is negative 13.4. If the temperature rises, does the relative humidity increase or decrease? This is like going down the backside of the mountain. It's always going to decrease because the air is descending. As it descends, it's going to get warmer because hot air, because as you go up in elevation, you're decreasing in temperature. So if you go down in elevation, then the humidity is going to decrease. So based on this, will the sinking air warm the dry adiabatic rate or the saturated adiabatic rate? Explain your response in 2 sentences. I don't want to tell you the answer, so hopefully you can figure that out. We're up here at the summit, and we've already determined that it's negative 13.4 degrees. Okay. And relative humidity is 100%. And we talked about this already, so we're just going to fill this in. 1,600 meters, temperature is 1 degree. And again, we're at 100% humidity. Down here, it's 17 degrees. It is less than the dew point temperature is 1 degree Celsius. So this is just filling in information, which is what it asks you to do. Based on your calculation, use the profile below and fill in any missing information about the labeled location. So the next one is going to be figuring out this Reno one. So what is the temperature of the air parcel once it reaches Reno at 1,500 meters? Show your work. So again, we're going to determine the change in elevation. So change in elevation. So we have 4,000 minus, it says it's a 15, so we're going to go from 4,000 to 1,500. So minus 1,500 equals 2,500 meters. Change in temperature. The dry adiabatic rate is 10 degrees Celsius per 1,000 meters. So we're going to say 10 times 2,500 divided by 1,000 is equal to, well, that was easy, 25 degrees Celsius. So we're going to add 25 degrees to this temperature. So we have 25 plus a negative 13.4 equals 11.6. So plus or minus is just minus. So 11.6 degrees Celsius. And again, the relative humidity is less than 100%. You don't need to worry about this part. All right, now let's look at the second worksheet. Okay. So the second worksheet, we're going to use the same. So if it's in Celsius, it's 10 degrees. If it's in Fahrenheit, it's at 5.5 and 3.5. Okay. So we're in Celsius in this particular case. So that's cool. We've already been told this is the lifting condensation level. So we don't need to figure out the relative humidity or anything like that. So we start by calculating the temperature of the air parcel at the following elevations as it rises up the windward side of the mountain. So if it was 30 degrees here, what is it at 1,000? Well, the dry adiabatic rate is 10 degrees Celsius. So 30 minus 10 equals 20. 20 degrees. What is it at 2,000 meters? So again, minus 10 because we haven't gotten to this magic line yet. So now we're at 30, 20, 10. So this would be 10 degrees. Okay. Then now we've hit the lifting condensation level. So now we're going to switch from the wet adiabatic rate, the dry adiabatic rate to the wet adiabatic rate or the saturated adiabatic rate. So this is going to be minus 6 now. So we get up to 3,000 feet. So this is going to be 10 minus 6 is 4. And then another minus 6, negative 2. Okay. After the parcel is descended down the lee side of the mountain to sea level, what is the temperature of the air parcel? Okay, so we're going to use dry, wet, and then as we come back down, this is the dry side of the mountain. So again, we're going to use the dry adiabatic rate. So this time we can use our change in temperature thing that we did before. So the change in elevation is 4,000 times 10 divided by 1,000 equals, gonna go with 40. So minus 2 plus 40, minus 2 plus 40 is 38 degrees. Why is the parcel now warmer than it was on sea level? What is the source of heat energy on the windward side of the mountain? I'm not going to answer that. You got to answer that one. Is the relative humidity decreasing or increasing? You should be able to answer that. On the lee side, you should be able to answer that. So I don't want to give you all the answers. That's how you do it. So I like to draw pictures. So even on these ones on the back, I would draw a picture. It kind of shows what they look like. A bunch of air, almost full of moisture, starts at sea level. Okay, so we start at sea level, that's 0 feet. Okay, and it's 15 degrees Celsius. Okay, if the dew point is 12 and the air moves up the mountain, what elevation will it begin to rain? How many meters? Okay, so in this particular case, instead of using, so we have 10 degrees Celsius per 1,000 meters, per 1,000 meters. But we're not going up 1,000 meters because we're only, going to lose 3 degrees. So we could do it like we did before and do the whole math. It was 0 feet and, we're going down 3 degrees. So change in elevation equals X divided by the change in temperature, which is 3 degrees. So 15 minus 12 is 3 degrees, right? Times 1,000. Or you could just drop off a 0 in each of these, which is the easier way to do it, in my opinion. So rather than doing all this algebra, okay, do it this way. So 1 degree Celsius per 100 meters is the same as 10 degrees Celsius per 1,000 meters. So we're going to go down 3 degrees. So we're going to go up 300 feet. Or sorry, 300 meters. What will the temperature of the air at the summit of the top of the mountain be? So now we want to know what it is at 1,000. And we already know, hello, 10 degrees per 1,000. So if it was 15 minus 10, or is it? No, it's not, because we have to stop here at 300 meters. And we have to use what? Oh, that's right, the wet adiabatic rate, because we've already determined this is the lifting condensation level. So it's not that easy. So you just don't get caught up. Draw the picture, put in the clouds, use this picture, create a new picture for each one of these, and see if you can figure it out. All right, good luck.